Alright, next we'll look at a typical minimization problem. In this case, we're just trying to minimize a quantity based on some constraints as opposed to maximize some quantity. So in this problem we have our objective function is to minimize the quantity z, which is equal to 4x plus 7y, and subject to the constraints that x and y must satisfy the following system of inequalities. The method of solution is the same if we're going to do this graphically, since this is a two-variable problem. You first graph the region of solutions, or the feasible set, making sure you identify the vertices of that set. And then again, we will just plug in all the vertex coordinates into the objective function to see which gives us the smallest value of z. And then that value of x and y is our decision, and the minimum or optimal value of z is the corresponding value of c. So again, if you watch the video on how to use GeoGebra to create these regions, you do the same thing here. The only difference in this case is that this region is unbounded, meaning when you're looking for all the points above the line 3x plus 2y, 3x plus y equals 20, which I have labeled here in blue, they also have to be above the line x plus 3y equals 30, and also above the horizontal axis and to the right of the vertical axis. So this region goes on forever to the upwards and to the right. And but it does have three vertices, which are listed here: 0, 20, 3.75, 8.75, and 30, 0. The point is we're trying to minimize the quantity. We obviously don't want to plug in points with large coordinate values. We want to use smaller values, and these vertices are all, in some sense, closer to the origin, 0, 0, than points far away in this unbounded region. This is a typical of a minimization problem to get an unbounded region like this, but keep in mind that it's not necessary. You could have a bounded region. For graphical purposes in GeoGebra, I did the same exact thing. I created a polygon, and then I just moved the upper right part of that polygon outside of the viewing window in GeoGebra so you couldn't see that. So I give you this image which makes it appear that it's an unbounded region. So again, with our problem, when our vertices known, we just plug them in. Vertex 0, 20 just means plug in 0 for x, 20 for y, into z, and that gives us the value of 140. Doing the same for the other vertices, the vertex 3.75, 8.75 gives us the minimum value of 76.25, because the other vertex of 30, 0 gives us a value of 120. And since we want the lowest value, our decision is to choose the values of x and y to be 3.75 and 8.75 respectively to give us our minimum value, or our objective, of 76.25.